Welcome to episode 41, Cryptography Requirements for I1, where we explain how sound encryption practices reduce exposure without slowing useful work. Cryptography is the discipline of protecting information through math and keys so that only authorized parties can read or change it. When applied consistently, it turns stolen disks, intercepted traffic, and copied backups into harmless noise. It also supports integrity by detecting silent tampering and authenticity by proving who a party really is. Organizations sometimes treat encryption like a final coat of paint, but it works best when planned from the start and verified in daily operations. In the I1 context, the goal is reliable protection tied to clear ownership, measurable controls, and exportable evidence. With that framing, cryptography becomes a practical tool rather than a mysterious art. Protecting data in transit means guarding information as it moves between browsers, apps, services, and partners. The expectation is simple to state and vital to enforce. Use modern transport encryption for every route where data could be observed or altered, including internal service calls and machine-to-machine links, not just public websites. Validate endpoints with trusted certificates to prevent imposters, and disable outdated protocols that allow downgrade names. Require strong mutual checks for sensitive links so both sides prove who they are before exchanging anything valuable. Monitor for plain text paths, unexpected ports, or legacy ciphers that slip back in during upgrades. Finally, document approved connection patterns so engineers know the safe defaults and can spot exceptions quickly. Data at rest encryption protects information stored on laptops, servers, databases, and backups. The standard is to make encryption the default, not a special request, so that new systems start protected without waiting for a manual step. Full disk or volume encryption helps when hardware is lost or retired, while field-level encryption can reduce exposure within shared platforms or analytics tools. Keep the decryption path narrow by limiting which services and roles can unwrap keys. Test recovery so encrypted systems can be restored without improvisation under stress. Track coverage with reports that show which assets are enabled and which are pending. Treat unencrypted stores as exceptions that require written justification, time limits, and compensating controls until closure. Certificates act as public identity documents for systems, so their lifecycle needs the same care as any other key. Begin with a catalog that lists where certificates are used, who owns each one, and when they expire. Automate enrollment and renewal so expiring certificates do not become outages. Require proof of control before issuance to avoid handing identities to the wrong party. Monitor for weak signature methods or long lifetimes that drag risk forward. Revoke quickly when private keys are suspected of exposure, and verify that clients react as expected. Keep renewal and revocation events in central logs so investigators can reconstruct the timeline. With this lifecycle in order, trust on the wire stays predictable. Algorithm choices and minimum strengths should be boring by design. Pick widely trusted building blocks, avoid homegrown inventions, and keep a short, approved list that engineers can follow without debate. Establish minimum key sizes and modes that meet current norms, and retire obsolete options with a clear schedule. Provide migration guidance so teams know how to move from weaker settings to stronger ones without breaking compatibility. Document default libraries and configurations for each platform you support so implementations converge on the same safe settings. Periodically review the list, but change only when there is a clear driver. The measure of success here is not novelty. It is quiet, dependable protection that stands up to scrutiny. Secrets management must live outside code repositories. Passwords, tokens, and private keys do not belong in source files, build logs, or container images. Instead, deliver them at runtime from a secret service that grants short-lived access and records every request. Limit who can read production secrets and separate duties so code reviewers cannot fetch live values. Scan repositories to catch accidental commits and rotate anything discovered immediately. Provide developers with easy paths for local testing that use mock or developer-scoped secrets so they never reach for the real ones. Make the secure way the convenient way, and leaks will decline. Hardware security modules provide physical and logical walls around keys. They generate and guard material inside tamper-resistant boundaries and can perform cryptographic operations without exposing raw keys to software. When dedicated hardware is not practical, use managed services that emulate similar guarantees and keep keys server-side, rather than embedded in application memory. Choose the level that fits the risk and the scale of your environment. Document which systems use hardware-backed protection and which rely on software stores, and explain why each choice is acceptable. Test failover and backup models so the protection you add does not become a single point of failure. Assurance improves when the hardest targets hold the most sensitive keys. Cloud key services simplify operations, but their inheritance model must be understood. Providers may encrypt storage by default, yet customers remain responsible for who can request decrypt operations and which workloads may use those permissions. Decide when to use provider-managed keys and when to bring your own, and record that decision with owners and use cases. Restrict access through roles tied to applications, not individuals, and alert on unusual use patterns such as decryption requests from new regions. Ensure backups of key metadata and policies exist in case an account issue disrupts access. Treat cloud keys with the same rotation, logging, and review discipline as on-premises keys, because the accountability remains yours. Evidence proves that cryptography is both present and working. Useful artifacts include configuration exports that show encryption enabled, key usage logs with timestamps and callers, certificate inventories with lifetimes and owners, and screenshots of policy settings in key services. Collect these items automatically on a schedule so the set stays fresh and complete. Organize them by topic so auditors can follow the story from requirement to control to proof. When teams can retrieve evidence in minutes, reviews move quickly and confidence rises. Evidence also supports incident response by revealing exactly which keys, certificates, and paths were in play. Common pitfalls cluster around convenience. Teams sometimes leave a debug port unencrypted because it is internal, store secrets in environment files for speed, or postpone certificate renewal until the next sprint. Each shortcut seems small until it becomes the only exposed route an attacker needs. Handle exceptions with a formal process that sets a reason, a mitigation, and an expiration date. Track them in a central register and review them often. Build guardrails into pipelines that block known bad patterns, like plain text endpoints or missing certificate checks. The program improves when the easy mistakes are made hard to repeat. Incident response for key compromise must be rehearsed, not improvised. Define triggers that treat suspected exposure as real until disproved. Identify which systems depend on the key, how to rotate or revoke quickly, and how to invalidate sessions or tokens that were issued under the old material. Coordinate communications so customers, partners, and internal teams know what to expect and what actions to take. Preserve logs before they roll over, and mark the time of actions to aid later analysis. After containment, review the cause, strengthen the controls that failed, and update the runbook. A fast, practiced response keeps a key event from becoming a long crisis. A reliable, well-governed cryptography program feels calm and repeatable. Data is encrypted in motion and at rest by default. Keys are created and rotated under clear roles, certificates arrive and renew without drama, and secrets never stray into code. Hardware and cloud services are used thoughtfully, with ownership and evidence close at hand. Exceptions are rare, time-bound, and visible. When questions arise, teams can show configurations, logs, and timelines that explain what is protected and how. That is the I1 standard in spirit and in practice. Cryptography that works every day, not only on paper.